So what's the one thing that separates a good engineer from a truly great one? It's not about writing code that never breaks. No, it's about mastering what happens when it inevitably does. Today, we're going to move past the basics and talk about how to master failure. You know that sinking feeling, right? Your entire test suite is green, you hit deploy feeling like a rock star, and then a real user does something you never, ever thought of, and the whole thing just falls over. So, what went wrong? Well, the culprit is almost always our obsession with the happy path. Look, testing for perfect inputs is essential. We have to do it. But it creates this dangerous false sense of security. Because the real world, it's messy. It is a total chaos of invalid data, expired tokens, and weird malformed requests. And if you're not testing for that chaos, you are just not ready for production.
To get ready, you really need a different mindset. So let's stop thinking about just testing and start thinking about running disaster drills for our API.
This is the core idea right here. I mean, think about it. You wouldn't trust a skyscraper's safety systems if they'd only been tested on a calm, sunny day, would you? Of course not. We have to proactively simulate a fire or a power outage just to see how the entire system responds when it's under real pressure. And this slide just breaks it down perfectly. Checking if the door's open, that's your standard positive test, right? The happy path. But simulating a fire, that's our negative test. We're intentionally sending bad data to see if the alarms go off correctly. And a power outage, that's an edge case, where we're pushing the system to its absolute limits just to see what happens.
Okay, so it's a pretty neat analogy, but why should you spend your valuable time on this? I mean, what's the actual payoff for you?
Here's what you gain, and it is huge. First, you prevent those super embarrassing late-night production crashes. Second, you dramatically harden your security because a ton of attacks actually exploit weak error handling. And third, you build unshakable trust. An application that fails gracefully and predictably is one that your team and your users can actually rely on. And trust me on this one. Every single minute you invest in these kinds of tests now will save you an hour of frantic debugging later. It's a direct investment in your own sanity. All right, let's get practical. How do we actually write tests that are specifically designed to provoke and then validate failures? First, the key definition here. Negative testing is, well, it's exactly what it sounds like. We're not aiming for a successful 200 OK response. We are deliberately hunting for a failure. But, and this is the key part, it's a specific, controlled, and expected failure. And the signals for those controlled failures are the 4XX client error codes. See, a code like 400 or 401 doesn't mean our test failed. It means our application succeeded. It successfully identified a bad request and rejected it properly. This is the win we're looking for. You can think of this as your tactical playbook. First, you brainstorm all the ways things could go wrong. Then, you define the exact error you expect to see, you build that broken request, you send it, and then you validate two crucial things: that the right status code came back, and that the error message itself is both helpful and secure. So here's a classic example. This test is simulating a client trying to create a new user but sending an empty request body. They completely forgot required fields like email or password. We fully expect the API to recognize this as invalid and correctly reject it with a 400 bad request. We're really just testing that our validation logic is on the job. And here's a little insider tip that separates the pros from the amateurs. A junior tester might just check if the status code is any 400 level error, but a top-tier engineer, they assert for the specific code. A 400 bad request means something totally different from a 401 unauthorized, and that precision is what makes your tests so incredibly valuable. Okay, now let's look at a critical security scenario. In this test, we're simulating a request to a protected endpoint using an authentication token that we know for a fact has expired. The goal here isn't to test the login system, it's to make sure our endpoint security is working correctly by rejecting the request with a 401 unauthorized status. What's so important to understand here is that this is way more than just a reliability test. It is a direct security validation. You are actively proving that your system can defend against broken authentication, which is one of the most common vulnerabilities out there. Now, as you start writing these tests, there are a couple of common traps that almost everybody falls into at first. Let's cover them right now so you can just avoid them completely. This right here is the #1 rookie mistake. The assertion on the left is frankly lazy. It tells you something went wrong, sure, but it doesn't tell you what. The one on the right is precise. It has intent. It confirms the specific failure you were testing for. Always, always aim for that precision. The next big pitfall is leaking sensitive data. Your tests must check that error messages are helpful to the user, but reveal nothing about your system's internals, like stack traces or database info. And the biggest mistake of all? Just not doing it. Sticking to the happy path and just hoping for the best. And let me tell you, hope is not a strategy.
Okay, we've covered a lot of ground. So let's distill all of this down into a simple, actionable checklist you can start using today.
This is it. This is your checklist for joining that top 1%. #1, actively test for failure. Intentionally try to break your system. #2, assert with absolute precision. Know the error you expect and test for that exact code. And 3, verify that your error messages are secure. And that really is the bottom line. This isn't some obscure high-level technique. It's a fundamental discipline. Master these 3 principles and you're not just a better tester, you're an engineer who builds more reliable, more secure, and ultimately more professional software. You got this.